So today's talk is going to be about solid-state physics. It'll be the first of a series of 2 talks on this topic. So today's part of this series won't talk about singular learning theory very much. It's meant to be an introduction to the physics involved here. So if you're familiar with that, it will maybe not contain a lot of new content. It'll be fairly elementary from a physics point of view. But the reason I want to introduce this background physics and then talk about how it relates to SLT is I think it's an excellent example of the underlying principle that would be involved if you were to apply SLT to engineering and understanding deep learning systems. So, as I'll explain, the whole science and engineering discipline of solid-state physics and more broadly condensed matter physics is about understanding the geometry of the level sets of the energy function that maps, say, the momentum of electrons, in the case of solid-state physics usually, to some real number. And where the level sets of that function are singular, you get interesting behavior, for example, with conduction bands in a semiconductor. And it's the relationship between the geometry of those level sets which determines the behavior of the material. And that's very similar to the way in which, say, Watanabe is talking about the behavior of a learning machine. It is also determined by the change in the geometry of the level sets as you change the value. Near the zero value, near the set of true parameters, but also elsewhere for other level sets. And that's the content of the theory of phases in SLT. And that's true also in materials. So there's a close analogy between the sort of global phase structure of a learning machine and the conduction, well, the energy bands and the behavior of electrons in a material in solid-state physics. So I want to, and it's not that relationship doesn't require sophisticated mathematics. It's you can get a long way with quite elementary observations in solid-state physics, and that's what I'm going to explain. Okay, so some basics. Solid-state physics, which I'll just abbreviate as SSP. So SSP, I'll release some notes for this talk. I didn't get time to upload them yet. Studies phases of matter with many strongly interacting components. E.g. crystals, or more precisely crystalline solids. It's strongly interacting because the vertices in the crystal, say a carbon atom, they interact strongly with the neighboring carbon atoms, and that's why we call it a crystal. So the reason that it's a separate discipline is that this class of materials, or rather this class of phases of materials, you have a very powerful set of tools from going from the geometry or the symmetry of the lattice to the electrical, magnetic, optical, and mechanical properties of the material. So, the source textbook for, I think the standard textbook for solid-state physics is Kittel. This is what I learned it from as an undergraduate many years ago. I think maybe that was like the 4th edition, and now there's the 8th edition. So what you'll learn if you open up Kittel is how to go from a description of the crystal lattice via density of states to properties of the material, say whether it's an insulator or conductor or semiconductor, and if it's a semiconductor, what kind, and so on. So let's see. So periodicity in crystal structure. Can be used to predict electrical And that's what we'll focus on today, magnetic, optical, and mechanical properties. We're focusing on electrical properties, and that's because the particular function whose level sets the geometry I'll be concerned with is the function that takes the energy, is talking about the energy of states of electrons interacting with the lattice. Okay, understanding this relationship. The foundation of the disciplines of engineering that are concerned with these properties of the material. And I think in the context of learning machines, it's interesting to note that maybe there are roughly two historical periods that you could divide this engineering discipline into. One is a kind of exploitation period where we just took the materials that we could find around us in nature, for example silicon, and then we tried to understand their crystal structure and what that meant about their electrical properties, and then we built on top of those properties to design, for example, circuits. But we're moving into a new, well, in addition to that, a very strong component of designing materials in modern physics. And that's, so my first example today will be semiconductors, and the second example will be twisted bilayer graphene, which is a sort of fancy modern material of much current interest. And that's more in the direction of, if you've heard of topological phases and this kind of whole discipline of engineering exotic materials on the basis of designing microscopic properties. Okay, so from exploitation to design. Okay, so let me give my first example. So there's a classification of materials into insulators, semiconductors, and conductors, which means high resistance, medium resistance, low resistance. That's a kind of coarse way of describing it. A more fine-grained way of saying what the difference is between these is to draw the structure of the bands, the electron bands, which I'll do in a moment. But I'll just note in connection with the previous point about engineering that the reason you've heard of semiconductors in connection with electronics is that the resistance of semiconductors can be designed. And the way that works is by introducing impurities, which just means some points in the lattice are occupied by atoms that are different to most of the crystal. So by introducing impurities in a process called doping. I'll just mention in passing that the doped atoms that you use to create semiconductors, they could be on the order of 1 in a million, or even 1 in 10 million or 100 million, and still substantially change the electrical properties of the material. Electrical properties here means the resistance. So from an atomic scale, somehow very few of the atoms are the doped material, but nonetheless it changes the global behavior of the material. And that's actually tightly related to a point that we're often trying to make in connection with SLT, right? Which is that singularities affect things far away globally, even though they're very tiny, somehow fragile local things. And the reason is the same. So you can change the topology of the level set drastically by small changes that are somehow in some sense far away, and so this is a sort of a relevant example of how small changes that seem innocuous at a very microscopic scale can add up and have global changes, and that's a common relationship between geometry and topology. Okay, so here's a diagram of the what the band structure looks like for these three classes of materials. So this is energy. So here I'll draw insulator, semiconductor, conductor. Okay, so well, the material is made up of many atoms in the crystal and many electrons, and as you know, the energy states, the energy of a single electron is quantized, but when you take a system which is a composite system of many billions or trillions of electrons, those quantized energy levels kind of add together and create a continuum of energy states, but maybe not a continuum that has no gaps. And so the set of possible energy levels of that very large composite system generically has the structure of bands. So I'll draw it like this. So the colored in part you're meant to think of as being, if you divided this up, you would see each line that looks like that is a possible energy level for an electron in this material. Now, two electrons can't occupy the same exact state, which is sort of important to the next point. So they're filled in a material. So this is these are meant to represent filled bands. That is, those are possible energy levels in which there is actually an electron in the material at this moment in time that occupies that energy level. In an insulator, maybe I should color this in more solidly. Okay, so this solid color is going to mean filled. And then up here, maybe I'll make it higher. So this is some other energy band, which from a theoretical point of view is just as good as these other ones, but in the particular material as it is right now, this is unfilled. There are no electrons in this energy band. And this is called the band gap. And in an insulator, it's maybe on the order of 5 electron volts. And these two bands, the top one of the filled bands and the bottom one of the unfilled bands, they have special names. This is the valence band, and this is the conduction band. And the idea, the reason it's an insulator, is that this energy gap, this band gap, is too large for, say, an incident photon to give an electron enough energy to jump across that gap. Of course, there are many photons hitting the material, and they will transfer energy to many different electrons. But for an individual electron to jump from one band to the other, it has to get all of it, and it's not going to get 5 electron volts from one of those interactions. So in practice, it can never enter that band, and that means it can't move through the material, hence it's an insulator. In a semiconductor, you have the same picture down here, but that band gap is smaller, on the order of 1 electron volt. Okay, so it is possible for electrons to make that jump. And in particular, if they're given a bit of help to make that jump by applying a voltage, for instance, then they will make that jump. And that's why semiconductors, so precisely p-n junctions, why those are the foundation of our computers. That ability to control the resistivity of the material by applying a voltage. And a conductor is just where there is no gap. Okay, so it's easy for an electron to just jump up to this conduction band, zip to the other end of the material, and hence it's a conductor. Okay, so the point of this is to explain how the structure of the bands, and in particular the band gap, is what determines the electrical properties of this class of materials. So now what I want to do is explain how the structure of those bands is related to, well, I won't say much about the periodicity and crystal structure, but how it's related to the density of states and the function that assigns to a given momentum, possible momentum for an electron, its energy. But I'll pause here for questions. Are there any about this picture so far?
You have an electron zipping from right to left, but no x-axis really in the sweat diagram.
Yeah, that's a good point. That's a nonsense thing to draw. Yeah. The x-axis in this picture, this is a typical kind of picture, but it's actually nonsense. I don't even know what that's supposed to mean. What is this axis? Yeah, there is no x-axis. That's right. I guess probably when people draw this picture, they usually have in mind the spatial axis of the material, I suppose, but that is kind of a bit, doesn't really make sense. So yeah, I agree.
It's like you're rastering along some phase space, filling it up as you go with electrons or something.
Yeah.
X-axis wise, doesn't matter. Anyway.
Yeah, I wonder. I guess strictly speaking, there can be no x-axis. That's the whole point of the exclusion principle. So it definitely does not exist, this x-axis. But maybe the picture is, yeah, I don't know. I agree.
Isn't the x-axis the distribution, as in the density plot? As in the x-axis would be number of electrons in that with that energy state, and
no, but
usually draw in the ground state.
Yeah, I think you could argue that you could use the x-axis to represent like the expectation of some observable, like the x-coordinate of an electron. So you could, you could maybe integrate this plot with some kind of expectation like that. But there definitely is no more. I mean, there is no such thing as the number of electrons in that state. Or I mean, you can talk about the expected occupation value, but it's really no, it's either 0 or 1. So I think, yeah, if you want to put an x-axis there, you'd have to think about it a bit harder. So I'll escape that, I think. So the x-axis is not a real thing. Okay, so my next example is twisted bilayer graphene. Let me see if I can get up a picture. Just one moment. So this is very cool. Wrong one. Bear with me. So I imagine some of you have seen the press around this before. Yeah, here we go. So what you can see on the left here are two 1 atom thick lattices, so crystals made of carbon atoms, so that's graphene. So like the blue layer there, it's a hexagonal lattice of carbon. That's what graphene is. And there's 2 of them that are layered on top of each other, and they're rotated relative to each other by some angle theta, which is, as it turns out, about 1.1 degree. And that's the magic angle. So in 2018, well, it's been predicted for a long time that graphene has sort of special electrical properties, and there was even some theoretical reason to think that its superconductivity might arise in bilayer graphene. But in 2018, it was an experimentalist group, if I get this correct, that discovered that if you layer graphene at exactly this angle, you get a superconductor, this two-layer material at about 1.7 Kelvin. So graphene on its own normally is an insulator, but if you arrange it in this particular, and if you arrange it at angle 0.5 degrees, it's an insulator, and 0.9 degrees, it's an insulator. But at 1.1 degree, there's a phase transition of some kind, and it becomes a superconductor. And low temperature superconductors is kind of the ultimate dream of condensed matter physics. So the amount of excitement around twisted bilayer graphene is absolutely off the charts. So what I want to do is write on this right-hand board here just a few of the terms that you'll find if you go reading about twisted bilayer graphene. The original paper, I'll put a citation in the notes, but you'll be able to find it easily enough. But there's some statements to do with TBG, twisted bilayer graphene, and then I'll sort of try and explain some of the terms that appear in those statements. So the first is from this 2018 paper. So it says, at 1.1 degree, the electron band structure of TBG exhibits flat bands. All right, the SLT, like alarm bells ringing, right? Flat. Flat bands near zero Fermi energy. And I'm going to underline a bunch of terms in green, and those are the ones I'm going to explain in a moment. So just kind of absorb the lingo by osmosis for a minute. Quantum oscillations in the longitudinal resistance. That's the left to right motion that I retreated from hastily on the previous board. So that's the resistance along the material, so the ratio of the current in that direction and the voltage indicate the presence of small Fermi surfaces near the correlated insulating state. Okay, that's one statement. Now, again, electron band structure, you should read structure of the level sets of the energy function, which for us is the KL divergence, right? So that's a kind of preview of where this connection is supposed to come from. Not from this original TBG paper, but from another one that's more recent and maybe more mathematical, is the following sequence of statements. So I haven't looked at the literature in the last year or so, so maybe the state of things has changed, but I think the exact reason or origin of the details of the superconducting state in TBG is theoretically still maybe not completely explained, or maybe there are competitive explanations. But one of the papers that's exploring this in more detail is making the following comments. Sorry, I just noticed the chat. Seems like the questions were answered. So one such feature is the, I'm going to mispronounce this, please correct me, Van Hove singularity, VHS. This was an old idea from solid-state physics. You'll find it mentioned briefly a few times in Kittel, in Moyer bands. So this is, I won't explain this, but this is part of the story with Brillouin zones and so on. Generally speaking, VHS with divergent density of states DOS This we're familiar with. This is exactly the same sense in which we mean density of states in singular learning theory. In 2D systems are associated with saddle points of energy dispersion. It's another term I'll explain. In K-space. So when a Van Hove singularity is close to Fermi energy, the increased DOS amplifies electron correlation. And that's one potential theoretical explanation for the superconductivity. All right, so I'm happy to take questions now, but the aim of the rest of the talk really is to explain these green underlined terms and get you to a point where you see past the difference in this jargon and or rather translate this jargon to our jargon, not to use the word jargon as a pejorative, to translate this into terms you're familiar with and recognize that what this is saying, the second bullet point, is simply, in our language, that the singularities of the set of true parameters, the worse they are, that's what controls the increased DOS. The worse they are, the more long-range correlations that you'll see in the system. And in this particular case, that determines the superconductivity. For learning machines, I mean, it's not that I'm saying there's something like superconductivity in a learning machine. I'm not claiming that, but the high-level observable property, which in this case is electrical, has a substantial change due to some fine-tuning of a parameter, the angle.
So, is superconductivity in learning machines superintelligence?
Yeah, you're the memes man here, Alexander. I don't know that probably makes sense. What's resistivity? There's no real analog of the lattice, right? So actually that's relevant to the argument about the diagram earlier. So the left-right axis in that diagram doesn't exist, but it's kind of implicit because the continuity of the band structure is due to the spatial dimension of the material, right? If you just had a single atom sitting there in your crystal, you'd have a discrete set of energy states. The wider and of course the material isn't infinite, so strictly speaking it isn't a continuum of energy states. The wider you make your material, in this case, the two-layer, the graphene, just the more area it covers, the more the energy spectrum looks continuous, but the role of the spatial dimension in the material is sort of invisible unless you think about it in terms of just that discrete versus continuous. So I don't know what the analog of the spatial dimension for a learning machine is, and therefore it's a bit hard to see what resistivity means.
It was just his joke, really, but do you have an idea what long-range correlations could mean in the learning machine point of view, or also not?
Yeah, I guess there is a spatial analog if you think about it from a sort of RG flow point of view between potentially different layers, right? So like the final layer and the early layers of a neural network, that would be potentially that could be potentially an analog of distance. This is getting a bit off track, but there is a sense in which there's an emergent renormalization direction that you can talk of in, say, Ising models. So probably there is an emergent sort of spatial direction in which you can talk about length correlations when you treat something like a large learning machine, at least one that comes from a neural network. But I don't, that's just speculation, so I don't know. No.
Would this be related to context lengths, or sorry, is that completely different?
Yeah, I mean, it would be kind of natural to use that. I mean, that is kind of one lattice that appears in a transformer, of course, but somehow the interactions are not, they don't change depending on the distance in your sequence of tokens, right? So the tokens are only a sequence somehow to you, human, feeding things in. The transformer just sees a sum over all the tokens, and whether it comes, I mean, there's the position embedding, I guess, which creates a kind of spatial dimension. So maybe, I don't know how to think about the role of the position embedding. Maybe that's...
I mean, the tokens aren't fed in randomly, right? I mean, every token has some text around it that's learned. I mean,
yeah, but it's like... It's the nearest neighbor interactions that kind of determine what a long-distance correlation is in a material like graphene, right? And so do nearby tokens, I mean, it's not like the effective energy that's attributed to that by a transformer really strongly correlates nearby tokens. I mean, it only does so through position encoding.
I mean, some texts have long-range correlations and some don't, right? There's like...
Yeah, but that's more a function of the data distribution than the model. So I would agree with that. I don't know how to map that onto this situation precisely. Okay. How am I doing? Okay. So I want to repeat something, one section from one of the earlier seminars on density of states, just because it fits here. So for those of you who've heard that, I'm sorry, but the next 10 minutes will be just a recollection of the density of states. So density of states. And then after I've explained that, I'll explain the other terms: dispersion relation, Fermi energy. I'll talk about the Fermi-Dirac distribution, and then I'll derive something about semiconductors using all of that as a kind of demonstration of how all of this actually gets used in solid-state physics to say a real thing about a real material. All right, so for a system with n discrete configurations, so here you could think about the states of electrons in our material if it was finite. N is finite here, or particle in a box, and volume V. Of course, it's a bit arbitrary how you define the volume, but anyway, I don't want to talk about that. So the density of states is, well, the number of states per unit volume at energy E. And in a discrete system, this is just a delta function. Right, so this is just 1 if E is equal to EI, 0 otherwise. And so it's just counting, so where the possible energy states are. Sorry. Where EI is the energy of the ith state. So for a continuous system, so I'm going to be pretty physicsy about this. That old lecture, I think it was seminar 5 or 7, there's notes attached to that, and in that I'm going into like Gelfand, Kirillov and generalized functions and telling you exactly how to do this properly, and so on. So I'll defer the the real math to there and just do the Kittel level story here. But the real version is what you'll find discussed in the... you actually need that to read through various sections of Watanabe, right? So that's sort of important for us, but not important for this story. Okay, so for a continuous system, the density of states at E is per unit volume the number of states accessible that you gain by increasing the energy by delta E. All right, so NE is the number of states. So the density of states is not the number of states. It's not the number of states per unit volume either. It's the number of new states that open up. So that's the number of states of energy less than or equal to E. Okay, so i.e. the number of new states accessible per unit volume when the energy increases from E to E plus delta E. Okay, so in a continuous system, of course, we actually deal with some kind of measure and we're integrating, etc. All right, so let me give you an example, and this is the example I want to use. It's enough to actually understand the simplest model of a semiconductor, which is a free electron gas. So for a free electron gas in d dimensions, of course d will be 3 for us for a semiconductor. Well, it's a free electron gas, so the only numbers I need to describe the energy is just the momentum. So the energy, the states are parameterized by the wave vectors. So that's just a vector in r to the d, which gives you the frequency in every dimension. And the energy of that state is p squared on 2m, or h bar. So m is the mass of the electron, h bar is what it is, and that's the dot product, k squared. All right, so the total number of states of energy less than or equal to E is just the volume of a d sphere with that radius, e to the half. So the total number of states of energy less than or equal to E is proportional to e to the d on 2. And if you look at the formula for dE, well, it's the derivative of n with respect to E. So just factoring out various pi's and so on, that's just proportional to e to the d on 2 minus 1. Okay, so that's the density of states for a free electron gas. Okay, what do I want to say about that? Well, it's an increasing function of E. The higher the energy, the more possible electron states you can have. But there are no special energy levels here, right? All energy levels basically are treated the same, except for 0. So 0 is the only singularity, critical point of this density of states. But every other energy level, right, there's just some expanding sphere, and the energy bands have nothing special to say about them. All right. Any questions about this? So how would you get a more complicated, interesting density of states? Well, you would have to have a more interesting energy function. And that might come from having the electrons interact with something, for example, a crystal lattice. And then the configuration of the atoms in the crystal would change the energy, perhaps in some way reflecting the symmetry of the crystal, for instance. And then the energy function would have a more interesting density of states, hence a more interesting band structure, hence more interesting electrical properties. So that's how that works. Yeah, any questions? I'm going to return to the rest of that dictionary now, and then do semiconductors. And indeed, that's what a Van Hove singularity is. So a Van Hove singularity, so this formula here would be proportional to just k1 squared plus k2 squared plus ... right? So you'll get a more interesting density of states, and this actually happens in real materials, if the density of states were, for example, a quadratic form of a different signature, right? So maybe it's got some pluses, and then it's got some minuses. That would give you saddles, or more precisely, singularities of different index, and they will have a different density of states, right? A more interesting density. Or you can have terms that are fourth powers. Those also appear naturally. All right, so let me come back now that I've recalled that material back to the rest of that dictionary, those underlined terms from those two papers. It's a glossary. The dispersion relation is just this function. E is a function of k. Okay, it tells you the energy is a function of the momentum. The density of states, well, I've explained what that is. The Fermi energy. So you might want to pop out of OrbCam and take a look at that board if you want to see how these terms fit back into that sentence. The Fermi energy is the energy of the topmost filled level in the ground state. This depends on the temperature, so maybe it's not like the ground state. You might mean by that the zero temperature ground state. I'll just skate over that. You'll see how it comes into the calculation in a moment, I guess. And then the other term was the Fermi surface. I'm going to come back to that in a second. But I want to introduce now the Fermi-Dirac distribution. There are citations in my notes. Maybe I'll just add one here. This is into Kittel 8th edition. So it gives the probability of an orbital at some energy being occupied in an ideal electron gas. Now, of course, in a real material, it's not a free electron gas because it's interacting with phonons, which are the perturbations away from the ground state of the sort of the lattice itself. So there's interactions between those phonons and in the electrons, and of course there's interactions with the electromagnetic field and so on. So it's not a free gas. But as usual in physics, it's useful to use the free gas as an approximation to vary away from. And as you'll see with this calculation I'll do in a minute, you can say something, some kind of interesting fact about semiconductors, even with this very kind of naive, I guess, assumption that it's a free gas. So this is useful. So it gives the probability of an orbital at energy epsilon being occupied in a free electron gas at thermal equilibrium. It's kind of baked into the expression, I guess. Here's the formula. So epsilon, the energy, minus mu, I'll say what that is in a second, and then this is +1. I'm not going to justify where that comes from. That's another talk. But I will note, so that's the temperature, T. Kb is the Boltzmann constant. Let us figure out what mu should be. It's one of the terms that's on the board, but we can discover which one by taking the limit. So in the limit as t goes to 0, this f epsilon, or maybe t is infinitesimal, given the previous talk. So f epsilon becomes 1 if epsilon is less than mu, and 0 if epsilon is greater than mu. Well, at 0 temperature, the Fermi energy is exactly the boundary between those states which are occupied and those which are not. So the mu is the Fermi energy at 0 temperature. Right? So the states below mu are filled, and the states above mu are not filled. There's the trademarked cow. Okay, so I wanted to say what a Fermi surface was, right? So I've just said that at temperature 0, some set of states are occupied and some set of states are not. Where does that set of states live? Well, a state is a configuration of a particular electron, and the possible configurations, in our case, in the free electron gas, are just given by the momenta. So the set of occupied states is a subset of the space of momenta. So in momentum space, I need to move over. So that's the momenta such that the energy is less than or equal to mu. Fill up a ball. The boundary or surface of which is the Fermi surface. Okay, i.e. Fermi surface means level set of the energy. And the energy is a map from the space of configurations, in this case the momenta, to R. Right, so in the SLT analogy, this would be K, and this would be W. Right, so the Fermi surface for us is a level set of the loss, or the KL divergence. All right, and so we have some idea that at a given temperature, as I said, the Fermi energy depends on the temperature, but at temperature 0, you have some set of occupied states, and that surface is telling you what it is. All right, and the real point here is, so think about this surface and what happens if you change one of the parameters. Okay, so where are the parameters here? Well, the parameters are in the energy. So as I was saying earlier, right? So you've got this free electron gas, has some simple formula. The Fermi surfaces there are just spheres, nothing interesting is happening. But if you turn on some interactions, for example, you turn on an electric field or a magnetic field, or you have a temperature gradient, that's going to change the energy, right? So you've got some space of energy functions. You're varying the energy. So for us, that might be a varying true distribution or some other part of the problem varying continuously. As you vary those parameters, the energy function, the dispersion relation, changes. And that will change the, if you just change the energy without changing the form of the energy function, you're just changing the level set of the same function. Or you can change the shape of all the level sets simultaneously by varying some of those parameters in the energy, and both of those are interesting. So from a point of view of a material, the linear response of a crystal to a gradient, as I said, but it's about the infinitesimal variation in the Fermi surface. That's what determines the properties that we're interested in, the things that we macroscopically think are interesting about a material, for example, the resistivity. This is just a direct quote from Kittel, I think. So the linear response of a crystal to an electric, magnetic, or thermal gradient is determined by the shape of the Fermi surface. I think to this audience I wouldn't quite say shape, I'd say topology and geometry. Because both matter and in slightly different ways. Right? But you'll see both discussed in these references. Because currents, so what's a current? A current is where an electron in the valence band, this topmost occupied band of the filled bands, is able to go up into the conduction band and zip around, right? That's a current. And of course it's stochastic, so it goes up, comes back somewhere else, and it's not a single electron going from one end of the material to the other, but the probabilities of those particular transitions is what controls whether there is a current, and if there is a current, how much resistance to it there is. Currents are due to changes in the occupancy of states near the Fermi energy. Which is what I just said. Okay. Yeah, I mean, there isn't a direct analog of electrons for a learning machine. Maybe there's something like Goldstone bosons. I don't know. They're like implicit objects you could maybe talk about, but it's not like there are explicit particles in the theory. Okay. Maybe let me just recall briefly how the DOS features in SLT. I'll maybe say more about that next time. How am I going for the time? Yeah. So yeah, let's move on to the second set of boards, and I'll recall how the RLCT arises from the density of states, just so you have some idea of how this connection is supposed to work. So follow me. So sort of just aside, density of states in SLT. So one of the formulas for the RLCT is that it is the scaling exponent of the density of states, right? So if you take the density of states, which Watanabe writes as V, so KL divergence, integrate over all this states, the configurations, the parameters, and integrate the prior, that gives you the density of states. And then if you take, well, think about in the example of the free electron gas, it was some power of T, right? And if I want to isolate that power, well, what I do is AT to the S divided by T to the S will give me A to the S, and then I take the logarithm of A to the S, that's S log A, and then I divide through by log A. That'll give me S, right? So that's all I'm going to do here. I'm going to take the logarithm of VAT minus VT divided by log A. A, I don't care, it's just some positive thing, and it's not 1. That isolates the exponent of the DOS, so it's like T to the S, kind of. And that's the RLCT, right? So in the regular case, it literally is a scaling exponent. I mean, that that example with the free electron gas is the regular case for us, right? So that's the RLCT is the scaling exponent of the density of states. Right, so more on that some other time, but that's where this plugs in. Okay, happy to take some questions, and after that I'm going to talk about semiconductors.
So the prior is the second derivative of the number of states.
The prior is the second derivative of the number of states. I'm not sure what you mean.
I mean, if I differentiate the number of states with respect to energy, I get the density of states.
Oh, I see. And then you mean you differentiate that again, and that kind of the coefficient there is.
Yeah, I'm just trying. I don't quite sort of see the link. I'm trying to interpret the prior in solid state physics terms.
Oh, I see.
Not quite there.
That would just be some kind of measure on the set of states, right?
Right.
So it would. Yeah, let's see. Yeah, actually, that gets in slightly complicated directions. That's because of the fact that two, say, electrons can't occupy the same state. There are more constraints on the prior, effectively, that you're going to be able to use in the physics setting of density of states than there would be here. Yeah.
They can occupy the same two states with the same energy. Right?
Yeah, that's right. Yeah, that's right.
Okay.
So this density of states, so in the SLT pictures is related with the measure on the per volume of the parameter space.
Yeah, that's right. It's sort of, if you were to draw a level set.
Yeah.
So it's sort of, as you increase so I'm going a little bit higher in the energy landscape, and that lets me climb a little bit further up the walls of the valley here. And the infinitesimal amount of territory, like if you project onto the bottom here, right? So it's not, so if you've got some sort of valley that's sitting above, and you, by that was the cutoff that was consistent with the previous energy, and then you allow higher energy and you go up, but that exposes, that increases the projection of that area down here, and it's the change in the area of the projection down onto the space of parameters, which is kind of what I'm trying to draw in this left-hand thing.
So is the volume, like the spatial direction, like volume in the physical system, is this directly analogous to the volume in parameter space? Like if it's a regular regular learning machine, then there's this notion of volume given by the Fisher information metric. Is this analogous? Is this directly analogous?
No. So the volume given by the Fisher information this is just the volume according to the prior, right? So those would be different, especially near the set of true parameters. And be careful when you say spatial direction. That's that's in momentum space, right? So the energy, the kind of space of parameters here in the physical setting is the space of momenta. So it's not volume of the physical system. It's like the volume of the kind of Fourier transform. Yeah.
I think I want to clarify that the density of states in SLT is actually the instantaneous increase rate of change of v of t. So it's a derivative with respect to t of that quantity. So there's a derivative missing in the definition on the board, if I remember correctly.
Well, you can formulate it differently and talk about it as a derivative, but I believe the formula for the RLCT is correct.
Yeah, the formula for RLCT is correct, yes.
Yeah.
So Jesse just told me, just want to check that, is as you move closer to the singularity, the density of states blows up, and the speed with which it exponentially blows up. That's the RLCT. Is that correct? Or the scaling exponent. Is that what you said?
Yeah, that's right.
Cool. Very cool.
Yeah, so that line of thinking has gone into in much more detail in that earlier seminar. Okay, so I want to explain semiconductors. Of course, the hidden message being that I'm about to do a lot of ugly truncations and approximations and derive a useful fact about electrical properties of materials. So then I will not be afraid to do similar ugly things to SLT, something like that. Okay, so let's talk about semiconductors. So intrinsic carrier concentration. So in a semiconductor, there's two types of carriers, two types of particles. You shouldn't get too attached to like particles as things with like real mass. There are holes that have effective masses and quasi-particles with effective masses and so on. Depends on the mathematical description. So the carriers here in one case are electrons. That's a kind of real thing. And then the other case are holes in the Fermi sea. Those have an effective mass, and they also carry a positive charge. Okay. So let's see. Where do I start? Okay, so we assume that epsilon minus mu, same meaning as before, is much larger than kBt. So epsilon here is the energy, mu is the Fermi level. You can think about this as halfway between the sort of in the middle of the band gap. Maybe I should draw a diagram. So here, so remember we're talking about a semiconductor. Here's the energy. This is the conduction band. That reaches down to energy EC. There's the valence band that reaches up to energy EV, and then the Fermi level is in here somewhere. Okay, and the energy gap is just the difference.
What does it mean? Fermi energy. It's the energy of the highest energy electron conserved here. So again, like this.
But this is different from the valence band.
So think about the free gas, right? The electron gas.
Okay.
The free electron gas is just a sphere.
Sphere in momentum space.
So the Fermi-Dirac distribution, in this case, well, maybe I'll write it out. So this was 1 divided by the exponential of epsilon minus mu on kBt
No longer
plus
smoothly
1.
distributed over high levels. It becomes a perfectly dense sphere.
I think we can hear you guys discussing, which is fine, but maybe you want to mute. Thanks.
Wow.
So under this hypothesis that epsilon minus mu is much bigger than kBt, I can just ignore this 1 is the point. Right? And so effectively I just get, this is approximately the exponential of mu minus epsilon on kBt. All right, so what's that saying? It's saying I'm considering an energy, say up here, or such that this gap is large compared to kBt. And that's not always true, but it's like, okay, this is our first shot at a theory describing semiconductors. So this will do. Okay, so that's the probability that a conduction electron orbital is occupied. That's an energy that's above EC. The energy of such an electron is, well, epsilon. I guess I was writing E before. Yeah, forgive me. I'm just going to stick with Kittle's notation. So this is energy. There's a lot of E's on the board, so maybe that's not such a bad thing. And the K is the wave number, as before. So it's going to be the energy at the bottom of the conduction band plus some term that comes from the momentum. You could think about it this way, that once you get up into the conduction band, how much extra energy do you have to actually propagate around? Maybe you use up all your energy just getting up there. That's one way of thinking about why this is a configuration that's I got plus this term. ME is the mass. Okay, so now we can use the earlier formula for the density of the state. So we're just going to treat an electron in the conduction band as a free electron. That's sort of embedded in that formula for the energy, right? So the density of states, right? So you could think about that as how many new states for a conduction band electron open up as I increase the energy by some infinitesimal amount. So that's d of electron at some energy. I left off these prefactor terms earlier, but if you think about it, they're the following. So this is not that interesting. That's just the constant of proportionality from earlier. And then you have the energy. And before it was d on 2 minus 1. Right? There was no term here. Free electron gas. I just had e to the d on 2 minus 1. This is now e. And d on 2 is 3 on 2. So d is 3. So that's just a half. Right, so that's just the formula from before. Okay, so now I'm going to see what the concentration of electrons in the conduction band is, just by integrating F against D. So I'm going to call that N. So that's the integral from the bottommost energy you can have to infinity, the density of states times this energy, dE. Right, if you think about it, the density of states was basically NE plus delta E minus number of states divided by delta E. So that means if I multiply the delta E over there, I have something that looks like this. And so what am I doing when I do this integral? Well, I'm just saying how many states are in this particular band times the energy that they have. Sorry, times the number, well, the number of electrons in that state, right? Times the probability of finding an electron in that state. So I'm going to go through every one of these energy levels, just multiply the number of electrons times the energy that they have. Sorry, I'm going to times the number of electrons times the probability, and that'll count how many electrons there are in the conduction band. Okay, and that's this number here, n. So let's do the integral. So what's that? Get all this junk. And then F had some junk? No. So mu minus epsilon d epsilon. Okay, well that's basically the integral of root x e to the minus x. Right, once we make a change of coordinates to make this x, this is going to change to some other thing. We can do this by integration by parts. We'll get one part that has an earth in it, and then we evaluate it infinity, that'll go away. So I'll just tell you what the answer is. So the answer is 2 me kbt 2 pi h bar squared to the 3 on 2, and then mu minus epsilon c, sorry, EC on kbt. Okay, that's the number of electrons in the conduction band. What does it depend on? Well, it depends on the effective mass of the electron. It depends on the Fermi level. It depends on this gap between the Fermi level and the electron band. And that's kind of it, and the temperature, of course. Now we can do a similar calculation for the number of charge carriers in the valence band. So it's basically the same. I'll just sketch how that goes. Okay, the equilibrium concentration of holes. The holes have an effective mass that you could derive. I won't do it. So there's like an mH for hole. Well, what is the... I mean, I need to know what F is. The density of states is going to be the same. But the F is just 1 minus the old F, right? The F for a hole is 1 minus F from above. I think I just wrote... F, didn't I? Yeah, just 1 minus F. Okay, and under the approximation that I'm taking, so that's 1 minus this thing. And if you just put them in the same denominator, divide through by that exponential, and use the same approximation as I did earlier, you'll get that this is just the, this is this. The density of states for a hole is the same kind of formula, but it has the effective mass for a hole, h bar squared, and then it's the difference between that energy at the boundary of the valence band and the given energy to a half. So now I guess in the first calculation my epsilon was something that lived kind of in this top group, right, in the conduction band. So this was up here for this stuff, and for this last board I'm doing, the epsilon is now down here. So I'm talking about this gap. Okay, so we just do the same thing, right? The occupation, so the density of hole states, it's just the same integral, p, now minus infinity, to EV, DHE, FHE, blah, blah, blah. Okay, and a similar formula. We don't really care about this formula independently. The upshot is what happens when you take the product of these two. And this actually informs how you engineer a semiconductor. And that's kind of the point of this little exercise.
The working.
Sorry? Oh, thank you, yeah.
Thank you.
Right, so basically the same kind of formula. So when I take n times p, the mu disappears. Right? So this is just some junk. I think maybe the fact that it's t cubed you care about, I forget. Right now I don't care. So I just get EC minus EV here, right? And that's EG, the energy gap. And this was the formula I wanted to get to. So the concentration of electrons in the conduction band times the concentration of the holes in the valence band is given by this formula. The interactions that cause electrons to jump from the valence band to the conduction band when they interact, say, with photons, is governed by these two numbers. So let me just finish this part by giving you a little taste of what's in this section of Kittel. Okay. Yeah, I guess it's a bit out of scope to justify the following statement. Okay, so there's a physical input here, which is that if you look at this quantity, the product NP is independent of impurity concentration. So remember I said that you create a semiconductor, well, one way to create them or to modify their properties is to dope them, to introduce some other atom into the crystal. And you can show that the product NP under these approximations is independent of the impurity concentration at a given temperature. And that's not a hard argument, but it's sort of would require a bit more physics to explain. Okay, so that's a physical input. NP is independent of the impurity, which you control, right? The introduction of a small amount of impurity right, which increases N, must decrease P, because that product is constant. And okay, what Kittel says here is this result is important in practice. We can reduce the total carrier concentration which is N plus P, and that's N plus some constant divided by P. Sorry, divided by N, because the product is constant, at least in the context of the changes we're considering. So you can increase that by introducing impurities, by raising N. Right? And this is called compensation. I don't know why. But anyway, this is a basic technique in the design of semiconductors, right? You want the total carrier concentration to be high, and this tells you how to do it as a function of this basic assumption of the electron gas being in both of the valence band and the conduction band a free electron gas, and this little calculation with the density of states. All right. So this is something to do with the relationship between bands of this energy function in this material. All right, and that's where I wanted to get to. So to summarize, there's an analogy between the energy function of electrons in a material in solid-state physics and the KL divergence in singular learning theory. We know in solid-state physics that many of the electrical properties of a material can be determined by the structure, the geometry, and the topology of the level sets of that energy function. And that's actually the foundation of the subject. Right? You can't do everything just by understanding density of states. Right? It's more complicated than that. But if you read Kittle's book, the density of states and how to reason about it, the Fermi surfaces, how their topology changes, pictures for the Fermi surface, how they relate to the crystal structure, that is like 3/4 of the course that I remember as an undergraduate. That's the bread and butter of solid-state physics. So this really is the foundation of an engineering discipline. And you don't need so much singularity theory for regular materials, but for things like the magic angle, potentially, and I don't want to overemphasize this because it's still ongoing research, right? But there are serious people writing papers explaining the ADE classification to solid-state physicists in order to understand the engineering of materials like twisted bilayer graphene. So maybe that can serve as a kind of template for how to go about trying to apply SLT to learning machines in the future. So the next talk next week, I'll go a bit more into some of the aspects I discussed today. I haven't decided exactly what. If you have opinions, then share them, and maybe I'll do whatever you say. Okay, thanks everyone, and I'll take questions.
So Dan, you just mentioned something about the ADE classification. What's the story there?
Yeah. So when you start, so there's a paper, actually it's the one I'm citing that I was quoted, the second one I was quoting from. The appendix of that paper is going through not all of the ADE classification, but so yeah, I forget exactly. Maybe the E types don't show up or something, but there is a discussion in that literature of, well, for the same reason ADE shows up in singularity theory, right? They're the simplest singularities you get that have modulus 0, so they show up for the same reason in this area. Yeah.
Interesting. Cool.
I don't really understand the last part about the last board. So the formula derived doesn't depend on impurity, but you're saying adding impurity would change. I mean, I understand the usual high school level explanation of doping and introducing different amount of carriers, but you're saying that process has something to do with the n times p formula. Or is the last part saying that it has nothing to do with that?
It's saying that I'm not sure I understand the question. So the idea of the impurities, as you're referring to, is that they would, depending on the type of impurity, whether it's an N or P type, would either increase the available amount of charge carriers or decrease it. But
it's hard for me to connect that last bolt with the second last bolt, that highlighted formula there.
Oh, the formula.
Yeah. So what does impurity have to do with that? That distribution, I think it's not normalized, but that.
Yeah, I'm sorry. This is a flaw in the presentation. So there's a missing piece here, which goes from this formula and then makes the physical deduction that I'm black boxing. So yeah, it's not very satisfying. I agree.
Okay.
Yeah. Let me see if I can.
Does
I
doping
can.
have anything to do with changing the Fermi surface, or is that like a completely different mechanism?
In this case, I'm assuming it doesn't, right? So it's kind of, yeah, I suppose it's considering a fixed level of doping and then varying that a little bit. So it's, yeah, let me see. Maybe I should just see if I can just see if I can explain this this step here. Yeah, the point is that this product, if you change the number of impurities, you'll change N and P, but the product will stay fixed. And that's deduced from thinking about the actual interaction between the photons and the electrons that are involved here. I can try and sketch the argument. I'll see if this makes sense to you. So here's the missing step here. So why NP is constant? So the population of electrons and holes is maintained by interactions with photons. So at some temperature T. So the photons generate electron-hole pairs at a rate AT. And this I could not explain right now. So some function of T times NP is the rate of the recombination. Oh, okay, no, that does make sense. Is the rate of the recombination reaction or emission. So electron plus a hole goes to a photon. So you could just think about the product as being the probability that some electron and some hole meet, I guess. And then there's some term proportional to the temperature. So what that means is that dN dt, which is AT minus BT NP, must be equal to dP dt. Let's see, does that make sense? Electron hole pairs. Yeah, that's right. Okay. So in equilibrium, dN dt and dP dt are 0. And that gives you that NP is AT on BT.
which means AT on BT is equal to the green box equation, which depends only on temperature and
That's right.
material property like the band gap.
Yeah, so yeah, but okay, now that I think about it, that doesn't seem to actually need this formula in the box, right? So I suppose you could read this combined as saying, here's an argument based on the equilibrium assumption of the number of holes and photons that suggests that the product NP only depends on the temperature, and that is consistent with this formula that's in the box, and that moreover computes it explicitly as a function of T. So you could read these as two separate derivations of the fact that the product NP only depends on the temperature, I suppose.
Yeah, sorry for holding out the session. I was just wondering where impurity factors into the whole derivation of the
No, you're right. This
formula.
This was a bit underthought. So maybe in combination with what I just said, the broader point is that from this formula for NP, you can then deduce other things as well as this observation, which, yeah, maybe now that I think about it, you could justify partly by other arguments. But this particular formula for the product NP, then later on in the section, Kittel goes on to use it to do other things. So maybe that's actually the stronger argument for the assertion that this calculation in terms of density of states and concentration and so on is telling you something physical. The particular example I chose, maybe this wasn't the right way to motivate it.
Yep, thanks for explaining.
All right, other questions?
What does doping look like in learning machines?
I suppose it probably means architecture, right? So, what are we doing when we design an architecture? Well, we're doing something like attempting, well, we don't know, I guess is the first answer, but you could conjecture that what we're trying to do is engineer the bands, or the equivalent of the bands, in order to create something that maybe has some properties like a conductor or a semiconductor, right? I mean, when we talk about learning being easy in transformers, maybe we mean that the electron bands don't have large gaps, right? Or the analog of the electron bands don't have large gaps. And so maybe when we say something like, it's easy to train X being, say, transformers, actually what we've done is introduce quote-unquote impurities into like just a pure feed-forward network or something, in a way that brings those bands closer together. I don't know. That would be my... Yeah, it's a good question. I think one should think about it much more carefully, but that is the kind of rough shape of an answer.
You say it's easy to learn because currents flow easier, and so somehow that's related to the learning dynamics involved?
Yeah, don't know about the analog of currents, but you could... So, learning... so if you're descending an energy surface when you learn, right, say by gradient descent, And if there are large energy gaps, well, what does that mean? That means that the bands, the analog of bands, will be something like collections of local minima of the energy surface in a given energy range. And so if there are large gaps, it'll mean it's quite difficult to move from some level set of the energy or band of level sets to some other band. So you don't have to posit an electron or some sort of particle to just think about, like, say, the Boltzmann distribution and moving between configurations, right? In this case, the relevant Boltzmann distribution is over energy states of the electrons, or over, over the momenta themselves, perhaps. So just being able to easily move between different bands of the energy that have high occupancy would potentially have something to do with ease of navigating the energy surface, right? And one of the reasons that transformers are successful is that they're easy to train, right? Meaning that you very often just get a predictable decrease in loss and you don't get stuck somewhere. So I guess you could maybe think about that in terms of structure of the bands.
I've seen formulation of the correspondence between thermodynamics and learning, Bayesian learning, that posit that the impurities are the particular set of data that is drawn.
Yeah.
In this analogy, then type of doping becomes choice of true distribution from which you draw the data. And I think the idea is that if you draw a different data set, if you choose a different true distribution, then you are sort of biasing level sets that are closer to that true distribution, and thus form sort of energy level. And if we want to discretize things like Dan say, it's sort of an order set of critical sets ordered roughly by the distance from the true parameter.
Yeah, I guess it's probably a little over-determined in the sense that, what does one mean by the analog of impurities? I mean, from one point of view, it's the thing you can control in your lab in order to engineer a given electrical property, which, given that you have these two inputs into the KL divergence, one is the true distribution and one is the model, you could think about engineering either of them in order to control the band structure and thus the sort of analog of the electrical properties. So yeah, maybe you could try and change the true distribution, or you could try and change the architecture. I mean, I guess I see the analogy to impurities being to do with the particular sample you draw, but I don't think it's a little bit not quite in the spirit of the reason why what you do when you introduce an impurity into a semiconductor, I think. Because that would seem to suggest that if you draw a larger sample, you just get rid of the impurities or something. No?
Drawing a larger sample would kind of just make the energy sort of state distribution concentrate on, becomes the true distribution, the engineered state, instead of just a perturbation from the pure material.
Yeah, but that feels like it's. I mean, you could also talk about a stochastic dispersion relation, right, where you have these additional stochastic terms in the energy, which would be the analog of the difference between K and Kn in our case. So maybe that's like another kind of impurity you could consider, but I don't know that. Yeah, anyway, That would be a good thing to think more about. Yeah.
Yeah.
Other
The
questions?
statistical literature will be the disorder, right? Like if you draw draw
Right.
two different data sets, it's a two different disorder, and the theory that we are going through today is like it's like a ensemble average version of that.
Yeah, that's right.
Right.
Okay, maybe we'll leave it at that. So thanks everyone. We'll continue with this topic next week, I think. Feel free to make suggestions for things to dig further into in this circle of ideas on the Discord. I'll post the 2 papers I quoted from earlier, and you can take a look at those. And that's it for today. Thanks.